Kia ora and welcome. My name's Tracy, and today we're going to be looking at the environmental impact of glass bottle production. This topic ended up being a bit longer than I expected, so I've decided to break it up into two different videos. Today we'll look at the raw materials of glass production, as well as the manufacturing process, and then next time we'll delve into recycling and reuse and how they can lower the overall environmental impacts. But if you want to skip ahead, you can check out the literature review below that I've written to accompany this video. It gives a good overview of the situation, as well as references some good sources that you can use to delve further into the topic. And finally, if you haven't already seen the first video in the series where we looked at the environmental impacts of aluminium can production, you can check that out up here. So without further ado, let's dive in. The primary raw material for glass production is silica, or silicon dioxide. And while it's possible to make glass out of 100% silica, it has a very high melting point of 2000 degrees Celsius, so soda ash is added to lower this down to 1000 degrees Celsius. But doing so makes the glass slightly water soluble, so limestone is added as well as a stabilizer. It increases hardness and chemical durability and makes it so the final glass product is insoluble. Other materials may be added in small quantities as well to affect the properties of the glass. For instance, alumina or aluminium oxide will make the glass more resistant to weathering, and the addition of iron will induce a green tint. The final product is known as soda lime silica glass, and it has a typical composition of 65% silica, 25% soda ash, and 10% limestone. Let's investigate the environmental impacts of each of these raw materials. Silica is seemingly an exceptionally abundant resource, making up a whopping 59% of the Earth's crust. It's the principal component of sand, the world's most consumed resource, with 50 billion tonnes consumed every year, an average of 18 kgs per person per day. However, not all types of sand are suitable for industrial purposes. Desert sand, for instance, is largely useless due to its smooth grains and high impurities. Glass production requires high-quality silica sand, composed of at least 98.5% silica and less than 0.35% iron. While coastal dune and riverbank sand are sometimes used, the most common source of silica sand is quarried quartz-rich sandstone. These sandstones are often found in areas of high geological activity and are extracted through open-pit mining. Extraction of silica sand from sandstone deposits begins with the clearing of vegetation and topsoil and the removal of any non-economic soil and rock. In environmentally responsible mining operations, the vegetation and topsoil is mulched and mixed together and set aside for future rehabilitation of the area, and this is crucial for restoring the ecological balance of the area post-mining. The extraction itself employs heavy machinery such as bulldozers and large shovels, as well as occasional explosive usage for sandstone access. Processing of the sand is typically conducted off-site and involves crushing, washing, screening, and potentially chemical treatments. Finally, the sand is fed into natural gas or propane-fueled dryers before being stored in silos and transported via truck and rail car to market. Very few studies have been conducted on the environmental impacts of silica sand extraction, particularly in the context of glass production. However, a 2022 study on the carbon footprint and cumulative energy demand associated with silicon extraction for photovoltaics concluded that the production of 1 tonne of silica sand extracted from high-quality quartz consumes 339 megajoules of energy and emits 22.7 kgs of carbon dioxide equivalents. Lower grades of quartz require additional purification steps, leading to an increase in energy consumption and emissions to 1010 megajoules and 47.9 kgs of CO2 equivalents for industrial-grade quartz, and 1580 megajoules and 86.7 kgs of carbon dioxide equivalents for low-quality quartz. Additionally, the washing process can consume up to 6,000 gallons or 23 cubic meters of water per minute, leading to concerns over water source depletion, as well as contamination by sediments and treatment chemicals if not conducted responsibly. Perhaps due to its false perception as a limitless resource, sand is one of the least regulated materials, resulting in environmentally damaging extraction practices in sensitive terrestrial, riverine, and ocean ecosystems. The prevalence of illegal and unregulated mining practices in many regions is accompanied by serious health and safety violations, posing risks to workers' well-being and contributing to key environmental problems. such as land degradation, loss of biodiversity, and deterioration of groundwater and natural drainage systems. The absence of adequate individual and collective protective measures exposes workers to the potential development of several diseases, including certain cardiovascular diseases, pulmonary tuberculosis, chronic obstructive disease, some types of neoplasms, autoimmune diseases, kidney disorders, and most notably silicosis, a progressive, irreversible, incurable fibrotic lung disease caused by prolonged inhalation of respirable crystalline silica dust. Quantifying the environmental impact of sand extraction, particularly the use of silica sand in glass production, is extremely challenging due to a severe lack of publicly available information. However, it's now understood that responsible sand extraction represents one of the major sustainability challenges of the 21st century. The unchecked demand for sand has escalated into a global environmental crisis, compounded by a general lack of awareness over the widespread impacts of extraction. Insufficient scientific research and policies to support responsible consumption and extraction practices exacerbate this issue, leading journalists to uncover the true scale of the impacts. To effectively address this crisis, we need to recognise that sand is in fact a finite resource and implement regulations for responsible mining practices to safeguard our ecosystems and mitigate the global impacts of silica extraction. Soda ash, or sodium carbonate, is a white, odourless, water-soluble salt that was historically extracted from the ashes of plants grown in sodium-rich soils. It was used in the Near East and Egypt as a flux in the production of glazes on small objects of quartz, steatite, and faience as early as the 4th millennium BC, and in glass production as early as 1500 BC. Today, most soda ash is produced synthetically from sodium chloride and calcium carbonate through the Solvay process. It involves several complex chemical reactions, including the precipitation of sodium bicarbonate, which is then converted to sodium carbonate through heating, producing calcium chloride as its only waste product. Ammonia is a key ingredient in the Solvay process, which requires large amounts of energy and fossil fuels to produce, contributing indirectly to the negative environmental impacts of synthetic soda ash. In total, each tonne of soda ash produced using the Solvay method consumes between 9.7 and 13.6 gigajoules of energy and emits 1.84 tonnes of CO2. A more environmentally friendly alternative to synthetic soda ash is natural soda ash, which is extracted either from the mineral trona or from sodium carbonate-bearing brines. Trona is most often mined through an underground room and pillar system, where a checkable pattern of rooms are carved out, leaving regularly spaced pillars left to support the overlying rock. The excavated trona is then brought to the surface for processing, which involves crushing and heating to drive off unwanted gases before adding water and filtering out impurities. After allowing the water to evaporate, the crystals are dried, screened, and sent to storage bins for transport. An alternative system involves injecting heated water into the underground ore body, dissolving the trona into a brine solution, which is then pumped to the surface for processing. This solution extraction method is purported to be safer and produce less emissions than traditional trona mining. Regardless of which method is used, the extraction of natural soda is significantly less energy intensive than synthetic soda ash production and therefore produces less emissions. Trona mining emits between 0.3 and 0.7 tonnes of carbon dioxide for every tonne of soda ash, depending on the quality of the trona. Natural soda ash is also significantly cheaper to produce than synthetic soda ash, and as a result, most new soda ash production capacity is based on trona. However, chemically exploitable trona deposits are geologically limited to just 3 regions. There are extensive deposits in Wyoming, USA, significant deposits in Turkey, and smaller, less chemically pure deposits in China. Currently, natural soda ash production is limited to Wyoming, USA, and Turkey. To remain financially viable in the future, synthetic soda ash producers are continuously looking to improve efficiency and reduce greenhouse gas emissions. Limestone extraction is a relatively simple process. After clearing away vegetation and topsoil, the limestone is removed through open pit mining, quarrying, or through a room and pillar type system, just as with trona. Open pit mining and quarrying methods often use explosives to break up the rock before loading the limestone onto haul trucks and transporting them to processing plants for crushing, grinding, screening, and occasionally washing to remove impurities. Diesel fuel and electricity consumption at the mines are the main sources of energy use and greenhouse gas emissions. A 2017 life cycle assessment on limestone quarrying in Thailand concluded that the energy use and greenhouse gas emissions for 1 tonne of limestone were 79.6 megajoules and 2.76 kgs of carbon dioxide equivalents, respectively. This is significantly less than the silica sand and soda ash. However, this data was sourced from a single mining operation. As is the case with soda ash and silica sand, the publicly available data for the environmental impacts of limestone extraction is severely limited. To manufacture glass, the raw materials are ground together into a powder and then mixed with crushed recycled glass known as cullet to reduce the energy consumption during melting. While raw materials and cullet melt at the same temperature, cullet's prior chemical reactions eliminate the need for extensive energy use in subsequent remelting, requiring only enough energy to reach a molten state. The proportion of glass cullet utilised in the production process varies amongst manufacturers. While a higher proportion is generally preferred, its use depends on the quantity, quality, and purity of the cullet available. Provided cullet of sufficient quality is available, some typical proportions for cullet use are 45 to 50% for flint glass, that's transparent glass, 60% for amber coloured glass, and 80% for green glass. Melting this mixture in a 1500 degrees Celsius furnace releases a significant amount of CO2 due to the thermal breakdown of soda ash and limestone into soda and lime. Following decomposition, the typical makeup of soda lime silica glass, ignoring any smaller additions, is 75% silica, 18% soda ash, and 7% lime. Once the molten glass has finished off-gassing and any impurities removed, it's cooled down to 1300 degrees Celsius, increasing the viscosity to a honey-like consistency, which will strengthen the final product. The molten glass is then sheared into drops and gravity fed into a forming machine at 1200 degrees Celsius. Blank moulds shape the necks of the partially formed bottles before they're transferred to blow moulds, where reheating and blowing yield their final shape. The bottles then undergo subsequent heat treatment to prevent the formation of micro cracks and then cooled slowly to reduce tension. A tin oxide coating is usually applied at 550 to 600 degrees Celsius, and then a polymer coating, for instance polyethylene, at 85 to 110 degrees Celsius to enhance mechanical strength and resist transit abrasion. Following a final inspection, the bottles are packed, palletized, and shrink-wrapped and dispatched to beverage manufacturers. Glass beverage packaging necessitates additional components like lids, labels, and glue, and these are produced by specialized packaging companies who dispatch these components individually to the bottlers who affix them to the glass bottles after washing and filling. While most of these materials are technically recyclable, particularly the metal lids, curbside recycling restrictions means that these tend to end up in landfills. And labels that are difficult to remove can even impact bottle recyclability. Unfortunately, there is a notable lack of available data on the environmental impacts of these ancillary components, as well as the downstream effects of the polymer coatings. Global glass manufacturing emits at least 86 million tonnes of carbon dioxide annually, with 75 to 85% coming from furnace fuel and the rest from soda ash and limestone decomposition. Each tonne of glass consumes between 4 and 17 gigajoules of energy, primarily to provide the high temperatures required to melt the raw materials. Energy and CO2 emissions vary depending on the amount of cullet used and the fuel mix. In China, where they typically use fuel oil, coal, and natural gas, they emit about 0.68 tonnes of carbon dioxide per tonne of glass produced, whereas European production, relying more heavily on natural gas, emits 0.47 tonnes of carbon dioxide per tonne of glass. Though one study claims that glass production could produce up to 1.4 tonnes of carbon dioxide emissions per tonne of glass, depending on the final glass product. Additionally, cooling processes dissipate 100 kgs of water to maintain machine temperatures within the operational range. In addition to raw material extraction and bottle production, the environmental impacts of glass bottles is also influenced by factors such as transportation and susceptibility to damage. Glass bottles have substantially more weight compared to other beverage packaging options of the same capacity, and therefore necessitate higher fuel consumption during transport. For instance, a 330ml glass bottle weighs 388 grams, which is significantly more than the mere 12 grams of an equivalently sized aluminium can. Moreover, glass is more fragile than other materials and therefore requires more protective layers to prevent breakage, and this further contributes to the environmental footprint of glass bottles. Quantifying the specific impact of transportation and damage is complex because it depends on a number of variables, such as the distances travelled, the modes of transport, the packaging design, and the sources of fuel. And unfortunately, comparative studies on different beverage packaging materials fail to delineate transportation and damage-specific emissions. However, some studies on bottle reuse have indicated that these factors are much smaller contributors to the environmental impact than raw material extraction and glass bottle production. Despite the public perception that glass bottles are the most sustainable beverage packaging option, studies have consistently shown that single-use glass containers produce significantly more greenhouse gas emissions than other materials, including plastic. However, as most of these adverse environmental effects stem from raw materials extraction and high melting temperatures, they may be mitigated through robust recycling and reuse initiatives, which is what we'll be looking at in the next video. If there's one thing I'd like you to take away from this video, it's understanding how little data and scientific research is available on glass production and raw materials extraction. These materials are ubiquitous, and yet we don't really know how badly the production affects the environment or contributes to climate change because there is so little transparency and a lack of government regulation of these industries. We'll delve further into these issues in the next video, but in the meantime, you can check out the literature review in the description below and the sources that I referenced there if you want to find out more. And if you haven't seen it already, you can check out the first video on the environmental impacts of aluminium cans here. Otherwise, I'll see you on the next one. Bye.